Hello students, this is Dr. Ben. I'd like to work through another problem that has to do with rotational equilibrium. This is one that doesn't have any numbers with it, but it is a chapter style problem. And it has to do with using a lever of sorts in order to hold up a heavy object. And we can see in this situation that we have a beam that is hanging from a rod that's inclined with the horizontal, and that rod is being held up by the pull of a rope in the horizontal direction. And in this problem, we're asked to figure out what is the expression for the tension that we need in order to hold up a beam of a certain size. And we want to do all this using symbols because we don't have any numbers. So basically, the force diagram for this problem is already complete, although we realized that there are two reaction forces at the hinge, and we could draw them on here, an F sub y and an F sub x. But those two forces do not cause any torque because they're acting at the pivot point, and so we don't have to consider them in our analysis. So the rotational equilibrium will be described by the equation that the net torque is equal to 0, and there are three different forces that cause torques, and so therefore there will be three different terms in our expression. So there will be torque due to the tension, plus the torque due to the weight of the steel beam, plus the torque due to the weight of the rod that's holding the beam up. All those three have to add up to 0. And if we let the symbol L represent the length of the rod, then we can go ahead and figure out what these quantities are. So the torque due to the tension will be equal to negative, first of all, because the tension will make the boom rotate clockwise, T times L times the sine of this angle. So that will be equal to theta so that'll be 180 degrees minus theta. Alright, then we have the torque due to the weight. So that will be positive because the weight of the I-beam will make the boom rotate counterclockwise. So that will be equal to W times L times the sine of this angle right here. So that'll be, well, that angle is the complement of theta. So that is theta, so that will be 90 degrees plus theta. And then the torque due to the weight of the boom itself will be positive because it will make the boom rotate counterclockwise, and that will be mg L over 2 times, oops, that was supposed to be the sine of 90 plus theta. Okay, so we need to solve this expression for the tension. So we'll have TL sine of 180 degrees minus theta is equal to capital W L sine of 90 degrees plus theta plus little mg L over 2 times the sine of the same angle. Alright, so in the back of the textbook are some trig identities that might be helpful here. So the sine of 180 minus theta is equal to the sine of theta. And let's check if the angle is equal to 90 degrees, then the sine of 90 is 1. And the sine of 90 plus theta is equal to the cosine of theta. So if theta is equal to 0, the sine of 90 is 1, and so the cosine of 0 is equal to 1. So we can rewrite this expression. TL sine of theta equals L times the cosine of theta times the quantity capital W plus mg over 2. And now we can see that the L's cancel out, and we can do a little more algebra and end up with T is equal to the cosine over the sine times the quantity W plus mg over 2, and I could write this as 1 over the tangent of theta multiplied by W plus mg over 2. Alright, it's a little hard to check our work since we don't have any numbers, but we can see that the expression in the brackets is a force, and so it should have the units of newtons, and the trig function has no units, and so I'm pretty confident that our answer has the proper units, which is that of newtons, and so that will represent the tension that's in the cable that supports the I-beam.